Hello, good afternoon to all of you. I hope all of you are doing well and all of you are in good health. So, in today's class, we'll move on to our next objective, that is to add to hexadecimal number using a subroutine, right? Now, you must have all known what is a subroutine or subfunction. It's a set of instructions that is capable of performing operation whenever it's invoked, right? Okay, so you need to always remember that a function is or subroutine is a set of instructions that's capable of performing an operation whenever it's invoked. So it's not capable of performing on operation on its own, right? So here what I've done is I've taken a previously written program and converted it into a program that has subroutine in it. So here what I need to do is I need to add two numbers using a subroutine. So just here I prepared a concept node. So A is initialized with 0, 6, B is initialized with 0, 5, and then I made a function call to add. So I've written call add. So this add is just conventional name of the function, right? Okay. So this later will be replaced by the absolute address of the function that lies somewhere else. So call add. Then a content of a is stored in f000h, right? Okay. So in add a, what we have is we have a plus equals to b. That means content of b is added to a, and the result is stored in a. Now, one of the observations that you must have also made is that whenever you are invoking the function add, neither you're passing any parameter nor you're receiving any parameter, but what you're doing is you are storing the result to result that is there in A to F000H, right? So this is happening because the scope of the register is throughout the program. So wherever you want to, you can initialize the register, and then you can get it used to perform any operation anywhere, right? So here I need not worry about the parameters that are being passed or the values that are being received, because the scope of the register is the entire program, right? So, but here what you need to mind is that you need to mind the control transfer that takes place between different functions. Okay, so that's why I've written only call add without passing any parameter nor receiving any value, right? So A is equals to 0, 6, B is equals to 0, 5, call add, then store the result in the accumulator, result that's there in the accumulator in F000H, right? Then we have definition for add as add is equal to add. We have A plus equals to B, right? Now this add will be placed somewhere else in the computer's memory other than the memory bytes belonging to the main program. So now let us translate the program using a 8085 instruction set. So MVI A comma 0, 6, MVI B comma 0, 5, call L1. So now what we need to do is we need to make a call to a function. So in case of high level programming, we specify the address of the function as we specify the name of the function. But here, since we are working with the absolute address, so straight away we will specify the address here. So this L1 label will be later replaced by the starting address of the function. Okay, and then sta f000h and hlt. Right. Okay. Now the function definition is as starting with L1. So A is as add B and return. So here return instruction is very much mandatory, because whenever a function call is being made, the return address is pushed into the stack. Okay, and then control transfer takes place, and then once the function is over, the return address is popped out of the stack, and the control is again back maintained into the main program. So this is very much important. Just remember that with each and every program that you have. With each and every program that you have, a stack is dynamically implemented that is called as a call stack that stores the return address where the return is to be made to once the function execution is over, and it also maintains the current status of the function. So it's very much important that whenever a function is being called, and whenever function control transfer takes place, and whenever the function execution is over, the return or transfer takes place. So that is done with the help of instruction that's called as return. So call, in addition to calling a function, what it does, it pushes the address into the stack, and whereas the return, whenever return is executed, it pops out the content of the stack, pops the return address from the stack, and then the control transfer is resumed. So that is the way how it actually works, right? So now, so what we have is, now we have a opcode representation of the same program. So 3 is 0, 6, 0, 6, 0, 5. As so opcode for call is CD, right? Just plain simple call is CD, right? So now this L1 is to be replaced with the absolute address of the function. So let us consider the absolute address of function is C050. So this L1 is now to be replaced by C050. Okay, the starting address of the function. Then 3200F076, right? And 80 and return is C9. So let the starting address of the program be C0C0. So C0C0 sorry. So at C000 we have 3E. At 1 we have 06. At 2 we have 06. At 3 we have 05. At 4 we have CD. So this is the opcode for the call instruction, right? And then at 05 we have 50. So C050 is the starting address of the function in the memory. So 50 here, C0 here. As I said, higher byte will go to higher address space, lower byte will go to lower address space. And then at C007 we have 32. This is the opcode for STA. And then at C008 we have 00, F0. Subsequently we have F0 at C009, and at C00A we have 76, right? So likewise at C050 we have 80, and C051 we have C9. Right, so this is the way how a program pertaining to subroutines are to be written. Okay, so this is a very simple program that is capable of adding two numbers using subroutines. Now, likewise, the next objective is to determine factorial of a number using subroutine, right? So here we have already then done this particular program in the past. So what we'll do is we'll simply make a call to factor, right? We make a call to a function that is called as factor. So factor is defined somewhere else in the computer's memory, like this, okay, right? So it's just fragmenting the previous program into two parts. We have the main and we have the function, right? We have the subroutine defined for it. So we have the same instructions are placed in this particular program as well. So it is simply a program that is capable of finding factorial of a number using subroutine. So just see how easy it is to write programs using subroutine in 8085. But what we need to always ensure is that we need to always ensure that the return instruction is placed in order to return the return the control back to the calling function, right? Okay, so this is very much important. So here, right? So here, this particular implementation is capable of finding factorial number using subroutine, right? So you can go through it in detail. Now, likewise, we have Fibonacci series using subroutine. So you need to execute all of this set of programs, right? So here also what we have done, we have fragmented the previous program into two halves, the main part and the Fibo part, right? Okay, Fibo part. So here we have made a function called the Fibo, right? So the control transfer takes place, the execution is done, and eventually again we need to have a return here so that the control is transferred back to the calling function and the program terminates, right? So just see, this is a very simple implementation of Fibonacci series and factorial using subroutine, or adding two numbers using subroutine, right? Okay. So in the next class, what we'll learn about is we'll learn about how to implement recursion. So I need to, if I want to solve problem using recursion, so how to do it, right? So this brings us to the end of this particular class. So hopefully you've understood. So please do implement these three programs using subroutine, and all the other programs till now we have just discussed using subroutine. Okay. So thank you very much.